When you look at acidic foods like vinegar, wine, and fruit juices, the acidity of all of these foods is due to a functional group called the carboxylic acid. Carboxylic acids are one of the most common and important biological and organic acids. These carboxylic acids are also found in a wide variety of other biological compounds that you might not initially think of as being acidic. Things like milk, even the fatty acids that we find in our fatty foods, and even meat includes carboxylic acid functional groups. In order for us to understand what carboxylic acid does in all these various biological molecules, we need to again learn about the naming, properties, and reactivity of this functional group. Our carboxylic acid, of course, contains that carbonyl unit of our carbon double bonded to oxygen, which we've previously seen in our ketones and aldehydes. However, what it adds is a hydroxy group in addition to that carbonyl. So it's almost like a combination of an aldehyde and an alcohol. And of course, as we've seen before, one of the ways that we can make our carboxylic acids is actually by oxidizing either our aldehydes or our alcohols. So it's one of our most oxidized organic functional groups. Let's begin with naming. Our carboxylic acid uses a suffix of oic acid. So for any compound that will include our carboxylic acid, we'll have that acid at the end indicating the acidic properties of our carboxylic acid functional group. As we look at a given carboxylic acid, so again, of course, we're just going to be looking at the number of carbons in order to give us our prefix, and then we'll use our oic acid ending for our carboxylic acid. So here we have our carbon chain. We've got 8 total carbons here, so that gives us the oct prefix, and this becomes octanoic acid. For our carboxylic acid, we don't need any numbers here because our carboxylic acid is always going to be the first carbon, right? Since this carbon only has one bond to a carbon, it's always going to be at one end of our parent chain. So we don't have to worry about putting any number there in our name. In terms of our priority, so the priority of our carboxylic acids is higher than all of our other functional groups that we've looked at so far. So our carboxylic acids take top priority over all other functional groups, including the aldehydes and the ketones that we've looked at recently. So if we have a compound with both an aldehyde and a carboxylic acid, let's go ahead and add a ketone here as well. So we're always going to start from our carboxylic acid. That's always carbon 1. And then we can just count out our chain from there. So we have 5 carbons to make this a pentanoic acid. And now we just have to add our individual substituents. So our ketone is now a branch at the 3rd position, so that'd be 3-oxo. Our aldehyde here is actually also going to get an oxo prefix to indicate that carbonyl carbon double bond to oxygen. So this would actually be 3,5-dioxo pentanoic acid, indicating those 2 different carbonyl functional groups here in our carboxylic acid. Again, of course, if we had hydroxy groups or alkenes, we would add those in as well, but we'd be always giving priority and the first number of our parent chain to that carboxylic acid. As I mentioned before, our carboxylic acid acts kind of like an alcohol combined with a carbonyl. So we have our highly polarized bond between our carbon double bonded to the oxygen, but we also have our highly polarized bond of our oxygen and our hydrogen, as well as, of course, our carbon and our oxygen, creating another partial negative charge, partial positive charge over here as well. Now, of course, with an oxygen and a hydrogen, that allows us to act as a hydrogen bond donor, and we're going to be able to form hydrogen bonds with other carboxylic acid molecules. So if I add on another carboxylic acid over here, you'll note that if we have two carboxylic acids next to each other, we actually have two different hydrogen bond possibilities. Right? Each carboxylic acid has that hydroxy group that acts as a hydrogen bond donor, and our carbonyl group that acts as a great hydrogen bond acceptor. So all of this hydrogen bonding leads to very high boiling points for our carboxylic acids, as well as melting points, of course, as well. So they'll have even higher boiling points than alcohols, because of course alcohols don't have that extra hydrogen bond acceptor to help to form those hydrogen bonds between our carboxylic acids. And of course they'll be higher than the other functional groups that we've looked at as well. This of course will also correspond with a very high solubility in water, at least for our smaller carboxylic acids. So in terms of both solubility and their boiling points and melting points, carboxylic acids are really at the top of the table when it comes to our organic functional groups. They have more possibilities for hydrogen bonding, and therefore more possibilities for interacting with water, and more possibilities for interacting between those carboxylic acid molecules. All of those interactions, again, increase our boiling points and melting points, and of course make it easier to mix with those water molecules. The reactivity of our carboxylic acid will of course be determined by our dipoles, but will also be strongly affected by the resonance within our carboxylic acid functional group. So with our two oxygens sitting this close to each other, as well as our double bond, we have essentially a conjugated system where our electrons can move back and forth between our oxygens. So if I'm going to draw my resonance structure, I can move my electrons from this oxygen to create a double bond, and move my electrons from the double bond up to that oxygen. This creates a new resonance structure where now our top oxygen is negatively charged with an extra lone pair. My lower oxygen now has the double bond to my carbon, and it's going to end up being positively charged as we've shared our extra electrons with that carbon there. Now this of course is going to be a minor resonance contributor because it has more charge compared to my initial structure here. But it does still indicate, again, that sharing of electrons between my oxygens. The other thing that we can see here based on this resonance structure is that my top oxygen is actually going to have a larger share of the electrons. Right? So we get a larger electron share up here, as indicated by that negative charge. Right? In our resonance hybrid structure, we'd have a partial double bond between each of these oxygens with a partial negative charge on my upper oxygen. A larger electron share, of course, also means that that oxygen is going to be a great nucleophile. So our carbonyl oxygen is the better nucleophile in this case compared to our hydroxy oxygen. The best electrophile here is going to be our hydrogen atom. So the hydrogen, of course, has the lowest electronegativity out of all of our atoms here compared to the oxygen and the carbon. So the bond between our hydrogen and our oxygen is highly polarized. Of course, our oxygen here is also positively charged, at least in this resonance contributor. So it's really going to be wanting to pull electron density away from that hydrogen. So that hydrogen is going to be very reactive. Of course, our carbon itself is still a good electrophile as well. So as we saw with our aldehydes and ketones, that carbonyl carbon is a pretty good electrophile because of that highly polarized bond to our carbonyl oxygen. So our carboxylic acids will see some similar reactions to our aldehydes and ketones, where we'll have some nucleophilic addition reactions with that carbonyl carbon and carbonyl oxygen. But of course, we'll also see another set of reactions that we focused around that highly electrophilic hydrogen. The electrophilic hydrogen on our carboxylic acid, of course, acts as the basis for the acidity of our carboxylic acid. So if we put a carboxylic acid in water, that carboxylic acid will react as a weak acid with our water, and we can actually deprotonate our carboxylic acid in order to form our conjugate base. So we can pull off that hydrogen using the typical acid-base reaction mechanism that we've looked at early on. And this will then produce our conjugate base here with our negatively charged oxygen. Of course, as we know, one of the things that makes this more acidic, of course, is that resonance, where once we form this conjugate base, we can then stabilize that negative charge by sharing it out between our two oxygens. So our double bond moves down here, our negative charge moves up here, and of course our resonance hybrid has our electron density shared equally between these two oxygens. So the high acidity of our carboxylic acid, of course, is based primarily on that resonance there of our conjugate base. As we saw in our first semester of organic chemistry, we can, of course, still modify and increase that acidity through things like the inductive effect, right? So if I add an electronegative fluorine here, that will pull electron density away and help to increase the partial positive charge on my hydrogen. Right, so with that extra fluorine, we'd be even more likely to react and produce our conjugate base, following again the typical acidity reasoning that we looked at last semester. Once we've deprotonated our carboxylic acid, we form a separate molecule in our conjugate base here. So we're actually going to call this carboxylate here, using a similar but distinct name from our carboxylic acid that represents the acidic protonated form. We're using that ATE ending to indicate this negatively charged carboxylic acid conjugate base, as opposed to our protonated and neutral carboxylic acid. This negatively charged compound will then usually also pair with a metal ion. So we might have like a sodium counterion, for example, to pair with our negative charge, so that we get that neutral ionic compound overall. So at this point then, for our particular compound here, right, we have our 4 carbons here, making this a butanoic acid. We also have that fluoro here, so this would be 3-fluorobutanoic acid. Once we've deprotonated it, we're going to be replacing this oic acid ending with our ATE, and we're also going to add in our sodium. So it becomes sodium, and then we have our 3-fluoro, and then this is going to be butanoate, and it's with that ATE ending there for our negative charge. So sodium 3-fluorobutanoate versus our 3-fluorobutanoic acid. Now the other interesting thing that happens here with our carboxylates is that, of course, with that negative charge in combination with, of course, our positively charged counterion, we now have an ionic compound that's incredibly polar and very water soluble. So we have an ionic component that's highly water soluble, whereas of course our carbon chain is still, it doesn't really like water, right? So we actually have then a very soluble portion of our molecule and then a less soluble portion of our molecule. This difference in solubility within our molecule is especially significant if we have a carboxylate group attached to a very long carbon chain. Right? So this entire region here is going to be very insoluble or hydrophobic, whereas, of course, we have the ionic portion that's highly soluble in water. We refer to this sort of molecule as a amphiphilic molecule, where it has both soluble and insoluble portions, or both hydrophilic, portions that love water, and hydrophobic, portions that don't like water and don't want to mix with water. These sort of molecules actually act as very good soaps. So what happens is our insoluble portion will look to grab other insoluble molecules, and they'll like to cluster together in these things we call micelles. So if this little ball here represents our highly soluble portion, and we've got our carbon tail at the end that represents the insoluble portion that wants to hide from water, these guys will tend to organize themselves so that we have a little sphere with all of our insoluble portions hiding inside, while our soluble portions point outside to our water environment. Right? So the water will be out here, all of our insoluble portions are hiding from the water, and then our dirt and grease molecules that are more oily and like our insoluble portion of our molecule will tend to go to the middle of this cluster. This is a micelle, is what we call this. And so then that dirt and grease can be washed away in our water as it's carried by this micelle that's created by our soap molecule. So this is a very practical use of our carboxylate molecule here. But it's also actually very important in the body as well. So the body uses a variety of different kinds of amphiphilic molecules to make these sort of micelle structures. This can be used for actually digesting foods, helping to pull certain foods out of your aqueous environment in the intestines. It's also used for building things like cell membranes, where we need that nonpolar barrier in the middle of, you've got our polar cell, polar environment inside the cell, as well as a polar environment outside the cell. So this sort of structure made by amphiphilic molecules is very important for more than just this soap application of our carboxylate molecule here. Our carboxylic acids are very important molecules. A large part of this is due to that acidity of these carboxylic acids, making them one of the most common biological acids. However, there are also a lot of other reactions that we can do with our carboxylic acid functional group, and many of these reactions will be very important in our organic lab as well as in our biological systems. So we'll look at those in the next lectures.